In section 3.5, we're going to shift gears just a little bit and not talk about derivatives at all. We're going to take a look back at limits, but in a different manner so that we can understand one more feature of graphs that might occur in certain problems. So what we want to do is take a look at horizontal asymptotes, but before we do that, we're going to do a quick little review of vertical asymptotes that you saw back in chapter 1. Vertical asymptotes, if you recall, the way we define them with a limit kind of definition is if we ever took the limit of a function as x goes to a particular value which we called a, and we found that answer turned out to be positive infinity or negative infinity, we knew there was a vertical asymptote at that point a. So how does that relate to horizontal asymptotes? Well, it's going to kind of have a relation, but let's take a first look at some horizontal asymptotes. So horizontal asymptotes, just like vertical asymptotes, are those invisible lines that you see dashed here that a graph approaches but never touches. And of course, they're horizontal in their nature, not vertical. So back when you studied horizontal asymptotes before, you might have encountered the terminology end behavior. The horizontal asymptotes, or the way a horizontal asymptote looks to the left, is the end behavior at negative infinity. The way a horizontal asymptote looks to the right of a graph is the end behavior at positive infinity. Ultimately, though, this is how we're going to define horizontal asymptotes. And you can see it's a little bit different from our vertical asymptote definition. And it is this. If we take the limit of a function, but now as x is going to infinity, and we get a number for an answer, we're going to know that that answer is a horizontal asymptote. The same can be said if we take the limit of a function to negative infinity. If we take the limit of a function as we are going out to negative infinity, and we get a constant as an answer, that's what that a is in both of these cases, then we're going to know that a is our horizontal asymptote. Or in other words, y equals a will be the horizontal asymptote. So we're going to have to check both positive infinity and negative infinity because of this end behavior idea. There's something going on to the left of the graph at negative infinity, and there'll be something going on for the graph to the right at positive infinity. So that's kind of the takeaway you should have. To identify horizontal asymptotes, we're going to take the limit as x approaches positive or negative infinity. So let's take a look at a couple basic examples so we can get to the true examples, I suppose, that we need to attempt. So I want to take the limit as x goes to infinity of 1 over x. So it might be hard just to jump to an answer just by looking at that. So I think the best way to approach this problem is to look at a table of values. And in this table of values, I'm going to let x get bigger and bigger and bigger. That's what this limit is telling us. X has to approach infinity, which is just a ridiculously big number, or the idea of growing without stopping. So what's going to happen with this fraction as we put bigger and bigger numbers in? Well, I'm going to start off with x being 100. If you plug in 100 into 1 over x, you'll get 0.01. If you plug in 1,000, you'll get 0.001. If you plug in 1,000,000, you'll get 0.00001. Ultimately, what you should be seeing in this pattern is as x grows to infinity, as x gets bigger and bigger and bigger, this overall fraction is shrinking. And it's shrinking down to what number? Well, it's shrinking down to 0. So, as it turns out, if you take a number, and it doesn't even matter if it's 1, 2, 3, 4, 5, a billion, if you take a number and divide it by infinity, so to speak, your answer is 0, because that overall fraction is shrinking down to 0. So there's two ideas that we're going to be dealing with in this section. How do we get answers to these limits when x goes to infinity? And then how do we take that answer and interpret it in terms of a horizontal asymptote? Well, just keep in mind what we said above over here. Horizontal asymptotes occur when we take the limit as x goes to infinity and we get a number for that answer. Here we got a number for our answer, so we know the graph of our function has a horizontal asymptote at y equals 0. Now, what if we take the limit again as x is going to infinity of x cubed? This one might be a little bit easier to see without having to do a table, but I'm going to still make a table nevertheless, just so you can see the pattern. As x gets bigger and bigger and bigger, as it approaches infinity, in other words, what's happening to the function x cubed? Well, when we plug in 10, we get 1,000. When we plug in 100, we get 1,000,000. And you can see right away, as x gets bigger and bigger and bigger, as it approaches infinity, x cubed is also getting bigger and bigger and bigger, so it's also approaching infinity. So again, the two issues we're going to grapple with in this section is how do we find limits at infinity, and how do we interpret that answer to be a horizontal asymptote? Well, here you see that our limit answer is infinity, but again, go back to the definition of a horizontal asymptote. If you take the limit as x approaches infinity of a function and you get a constant, that's what that a is, it's just a constant, then that's your horizontal asymptote. Well, we're getting infinity as an answer. That's just a number that's growing without bound, just the never-ending growth. So since that's the case, we're going to interpret that answer to mean there is no horizontal asymptote. So, armed with those two examples you saw on the last slide, where if we take a number and divide it by infinity, basically, we get 0. And then the other example where if something's just growing without stopping, that becomes infinity, we should have enough to attempt these more complicated problems. So I want to take the limit of this function as x goes to infinity. So you might remember a little property from limits back from chapter 1, where if you're taking the limit of a fraction, we can take the limit of the top part separate from the bottom part. If we take the limit as x goes to infinity of 3x, you're really just having to ask yourself, what would be 3 times a very large number, or 3 times infinity? Well, of course, that would be just another really large number, and that's infinity. If we take the limit of the bottom piece separately, what would be infinity squared, so to speak? Well, that's just a very big number. If we multiply that by 2, it's still a really big number, which we call infinity. And if we add 1 to that, that's still going to be infinity. Ultimately, what we're discovering here is we're getting infinity over infinity. And that's going to bring up a term you saw back in chapter 1, an indeterminate form. Back in chapter 1, you guys saw the indeterminate form, and I'll put chapter 1 right here. You saw the indeterminate form 0 over 0, which meant you had to do some more work. We're going to add one more to that list, and that is the indeterminate form of infinity over infinity. Once we kind of know that, we just need to apply the idea of doing more work, which we'll get into in a second. If you're just curious, this is totally for your own, I guess, reference. There actually are other indeterminate forms, but we're not going to look at those. I just kind of wanted to give you the list of other indeterminate forms there are, just as a way to be complete with this. But ultimately, we're just going to focus on the 0 over 0 indeterminate form and infinity over infinity indeterminate form. So back to the problem at hand. The way I'm going to approach this question is with this idea here. Who is approaching infinity faster? And what do I mean by who? I mean the top or the bottom. Is the top approaching infinity faster, or is the bottom approaching infinity faster? Well, to answer that question, we're going to keep some things in mind here. The numbers in front of our variables, which we call coefficients, do not greatly influence the growth. In other words, taking infinity times 3 isn't going to really make too much of a difference in terms of that final answer. But this is the key. This is the part that I would definitely highlight and take note of. Higher powers approach infinity faster. That is to say, 3 times infinity is not as big as 2 times infinity squared, like you see in the bottom. And that's the answer to the question. The bottom is growing much faster than the top. They're still getting to infinity, but the piece that's winning the race, I suppose, is the bottom. Since the bottom has a square for its x, that's going to get to infinity way faster than x, just an x. So what does that mean? Well, if the bottom is growing much faster than the top, just like you saw in that last slide, if you take something small and divide it by something very big, we're going to get 0 for that answer. So to round out this problem, we can extend this answer to understanding where there's a horizontal asymptote, and since we're getting a constant as our answer, our horizontal asymptote is at y equals 0. Okay, so one more example. This one I'm going to kind of break down into a bunch of steps, unlike this one in the top. This one in the top, I just wanted to go over this idea of things growing and which ones are growing faster or slower, but this problem is going to be more along the lines of how you guys will show the work for these problems. So very important thing you should have taken away so far from this lesson is we're looking at the highest power in the numerator and the highest power in the denominator to determine the limit. So the thing we need to keep in mind is only the leading term of a polynomial affects the limit. In other words, this is the highest power. The highest power, which is just another way of saying the leading term, is the only thing that really affects the limit. So I'm going to go ahead and gray out the positive x minus 7. I guess it's still there, we can't just make it disappear necessarily, but all we're focusing on are the highest powers in the top and the bottom. The thing we do need to keep in mind though is negative coefficients do affect the limit. The number itself doesn't really affect the limit like you saw up in the top, but definitely a negative will affect the limit. So what are we left with? Well, we're left with an x cubed in the top and an x squared in the bottom. If we kind of ignore that x minus 7 and just focus on our powers here for a moment, we can reduce those powers, just like regular algebra problems. If we have an x cubed over an x squared, we can cancel the 2 x's in the bottom with the 2 in the top, and we'll be left with 5x in the top and negative 2 in the bottom. Now we can attempt to take this limit. If we plug in, so to speak, infinity, 5 times infinity would be infinity. If we divide that by 2, that's still infinity. But since that's a negative 2, our final answer will be negative infinity. Again, all these problems have 2 issues with them. What is the answer to the limit? Here it's negative infinity. And what is the answer for our horizontal asymptote? Well, for there to be a horizontal asymptote, we need to have gotten a result that is a constant. Here it's infinity, so we interpret that to mean there is no horizontal asymptote. Okay, now that we saw that last problem where I broke down the limit, or the process of taking a limit, to a bunch of steps, I'm going to clean up that process so that now we can attempt these problems, make it a little more efficient. So on this slide, we're trying to find the horizontal asymptotes for all these functions. So the concept that you need to keep in mind when you're trying to find a horizontal asymptote is to take the limit to infinity. So we're going to take those same steps you saw in that last example and kind of clean it up a little bit so you can have those steps. So the very first step, which I'll label here as step 1, is to only consider the highest power in the top and the bottom. Okay, so now that we did that, the second step that you should have observed in that last example is we need to simplify. And usually there will be something to simplify. If we simplify this expression, we'll just be left with 1/3. The third step, once you simplify, is to take the limit. If we take the limit of a constant, you'll have to recall from chapter 1, we just get a constant. It doesn't matter if x is going to infinity because there is no x to affect our function. The limit as x goes to infinity of 1/3 is simply 1/3. So keep a couple things in mind as you do these problems. You'll notice I wrote the limit notation in every step till we actually took the limit. So be good with your math notation, or that might end up messing you up on your problems as you attempt them. Okay, so now that we have the answer to the limit problem, now we can interpret that answer to figure out if we have a horizontal asymptote. If you ever take a limit to infinity and get a constant as your answer, that will be your horizontal asymptote, which in this case is y equals 1/3. Okay, so let's do these 3 steps on the rest of these problems. We're going to consider only the highest power in the top and the bottom. Again, make sure you're writing your limit notation here. We're going to simplify the expression, that's step 2. So the x in the top will cancel with one of the x's in the bottom. And then we're going to take the limit. If you plug in, so to speak, infinity cubed times 2 would just be infinity. If you take a small number like a 3, or really any number, it could be a billion if you wanted. If you take a number and divide that by infinity, you should have realized that that answer will be 0. If you take something small and divide it by something extremely large, that approaches 0. So the answer to the limit is 0. How do we interpret that to be a horizontal asymptote? Well, we know since we got a constant as our answer, our horizontal asymptote is at y equals 0. Okay, next example. Again, we're going to just disregard the things that are not important really, or in other words, only consider the highest power in the top and the bottom. Next, we're going to simplify the expression. You can see the x to the 4th cancel out very nicely, so we'll go ahead and cancel those out. And we're left with 6/5. The limit of a constant is just that constant. So don't get that confused with derivatives. It's something you can easily confuse with derivatives because we've shifted back to the limits. So the limit of a constant is just that constant. Since the answer to our limit question was a constant, we know we have a horizontal asymptote at y equals 6/5. The last example is just the same kind of example as you've seen before, but a little bit weirder looking, but the same 3 steps still apply. If you want to find a horizontal asymptote, we need to take the limit as x goes to infinity. Then we're going to only consider the highest power in the top and in the bottom. Here, though, we have a square root in our function, so just like you've hopefully been getting used to this year, we don't really want to keep that as a square root notation. We want to change that to a power, which would be 1/2. When we simplify that x squared over x to the half, we're going to take that power of 2 and subtract the bottom power of 1/2. If you recall back from algebra, when you want to simplify an x divided by an x, we take the powers and subtract them, which would be x to the 3/2. We've simplified our expression, now we can take the limit. Infinity to the 3/2 is just infinity, times a -3 is negative infinity. And if you take negative infinity and divide it by 20,000, you'll still be left with negative infinity. Okay, so that's the answer to the limit portion of the problem. We need to interpret that answer to figure out if we have a horizontal asymptote. And since we did not get a constant, we didn't get a number as our answer, we know that that means there is no horizontal asymptote. This slide is going to serve as a kind of overview of the 3 different types of limit problems you'll be doing when you're taking the limit of a rational function or a fraction as your function. But just keep in mind, this is kind of an overview of the 3 types of problems. When you do your limit problems, you still need to show all the steps like you saw in that last slide of examples. So maybe you observed that if the greater power is in the top of a fraction, we'll end up with an answer of either positive or negative infinity. This problem I could break down into all the steps like you saw in that last slide, but just to avoid all that work, I'm just trying to give you an overview of the 3 different types of problems. You can see that essentially we're going to end up with infinity, a very large number, over the number 3, in a manner of speaking, a smaller number. Ultimately, infinity divided by any number, as long as it's just a number, not 0, is just infinity. Maybe you observed in some of these examples that if the highest power is in the bottom of a fraction, then that limit is going to be equal to 0. And I'll kind of just reverse the case you saw above. If the bigger power is in the bottom of the fraction, we're essentially just taking a small number and dividing it by infinity. If you take something small and divide it by a very large thing like infinity, that limit approaches 0. One other type of example you might have observed in the ones I've done so far is, what if the highest power in the top and the bottom is the same? Well, you might have noticed that the answers there were just the ratio of the leading coefficients. That is, the answer was just the number in front of the highest power in the top divided by the number in front of the highest power in the bottom. So again, this slide, just kind of an overview of the 3 different types of problems you'll see when you're taking the limit of these fractions or these rational functions. But again, you'll still need to show all your 3 steps of doing these limit problems. Okay, we have one more example, even though it's split up into 2 pieces here. One thing I didn't really mention in all the examples I've done up until now is, if you go back to the very first slide, we were supposed to be taking the limit to positive and negative infinity to determine our horizontal asymptotes. What I'll have you do, if you want, is you can pause the video and refer back to those examples. But if you look back at all the examples, just imagine doing those problems where you're taking the limit to negative infinity as well. The thing you should notice is all of those answers would be exactly the same. They wouldn't be any different. So I never bothered showing that. I waited up until now to mention that. But that's an important thing to point out. We do need to check for the limit going to positive and negative infinity. It's just all the examples I've done up until now, the negative infinity answer would have been the same as the positive infinity answer. But maybe in this last example, that won't turn out to be true. So I'm going to go ahead and take this problem, and I still want to find the horizontal asymptotes, but I am going to split it into the positive and negative infinity like we should have. Okay, so the steps are still the same though. We're only going to consider the highest power in the top and the bottom. And then we're going to simplify. If we take the square root of the bottom, 2 things are going to happen. We're going to end up with a positive and a negative, like we usually do when we take square roots. And then when we take the square root of 2 times x squared, I can split that. The square root of 2 is just the square root of 2. The square root of x squared is x. Now we can attempt to simplify this one more step. But one thing we're going to observe here is that when we simplify this, we're only going to keep the positive answer because x is approaching positive infinity. We're going to the right, so we don't want to keep the negative part of this answer. We just want to keep the positive part of this answer. Once we do that, now we can do the algebra simplification here. The x in the top will cancel with the x in the bottom. And that's just a constant, not a nice looking constant, but 3 over the square root of 2 is just a constant. So when we take that limit to infinity, it's just that constant. So our process has changed, not really, but there's one extra little step here in that we're needing to decide which sign to keep. We keep the positive because x is approaching positive infinity. Okay, so how is that going to be different in our other part of this problem where we're going to negative infinity? Well, luckily the process is still the same. We're still going to end up with this same expression, 3x over the plus minus square root of 2 times x. But just like the one above, in this case though, we're only going to keep the negative portion of our answer because x is approaching negative infinity. So it's an important thing you're going to have to keep in mind anytime you end up with this positive negative. If you're going to positive infinity, we keep the positive. If we're going to negative infinity, we keep the negative. But again, luckily the steps are still the same. We consider the highest power in the top and the bottom. We're, I guess, adding one extra step in terms of figuring out, do we keep a positive or a negative? But now we can go back to the next step. simplify your expression, the x's will cancel, and then we can take the limit. The limit of a constant, which -3 over square root of 2 is just that constant. So you can see we did get two different answers in this case. They are basically the same answer, one's positive, one's negative, but we are getting two different answers. Unlike all the examples I did before, we would have got the same answer whether it was positive infinity or negative infinity, but we still had to really check for both. In this case, it's a good thing we split it up into the two because we did get separate answers. To verify these two answers, unlike the problems I've done in the past, I'm going to go ahead and give you a graph of what this function looks like. And you'll notice we are leveling off, which means we have a horizontal asymptote. Our function is leveling off, so it's approaching some value, and that value is 3 over the square root of 2. That's our end behavior to positive infinity. You'll also notice at the bottom, it's also leveling off, and it's leveling off to approach the value of -3 over the square root of 2. That would be our end behavior to negative infinity.